So today it's a pleasure to be here and talk to you guys about plant breeding genetics and where we're at and where we're going. So what I'd like to talk to you guys today about is the techniques that we use in some of our breeding programs across Australia, and also some of the ways that we reinvest the income we derive from EPRs in a new technology, and how we can hopefully increase that genetic gain or yield increase quicker. The whole idea of everything we do at AGT is to get higher profitability into farmers as quick as we can. That's the overarching idea of what we do. So through plant breeding, we hope to achieve that. So a bit of a history about AGT. So we started in 2002. Now before that, from 1880s to 2002, wheat breeding and most of plant breeding was actually publicly funded. So the governments around Australia all said this is starting to get a bit too expensive. We can't actually put as much money as we'd like to into these breeding programs. So public companies were formed, private companies were formed around Australia, AGT being one of them. So we started in 2002. We went bankrupt about 3 times there from about 5 to 10 years, and now we're actually in quite a strong position where we have about 60 odd staff, and we're ever growing around Australia in 4 main locations that we call breeding centres. Some of the varieties that you guys have seen or in the marketplace previously would be Mace, Scepter being the new benchmark. H45 was one that we released. It was actually out of a hybrid breeding program. The hybrid program didn't last, but one of the parents actually stood up really well. So if you do remember that one. Cutlass was one that we released at the Facey Group field day probably 2 or 3 years ago. Yep. And Bremer, which was the first wheat that we released out of the WA breeding program. So that's a bit of a quick history lesson, and I thought I'd show you. So we took over the Roseworthy breeding program, which was over 100 years old. So we got quite a good background of breeding for over 100 years. So what we've done is we've put a nice trend line through the yield gain, or what we call genetic rate gain. So you can see here, this is the part that I wanted to focus in on. Just before the EPRs were introduced, it was still publicly funded. Not enough money for it actually to be serviceable was being poured into the programs, so it stagnated or plateaued. Once AGT turned around and became a company, you can see that it started to kick up here, and now with Mace, and obviously Scepter will be a little bit above Mace as well. So that genetic gain is really starting to happen. The investment from the EPR models is really actually kicking up, and we are getting that higher profitability that we've been looking for. But before we go too far into the technology and everything the fun techniques that we use at AGT, I thought we'd do a crash course on breeding, just so you guys can actually understand hopefully what we're talking about. So breeding is the deliberate crossing of individuals to produce a new crop variety with desirable properties. That's the overarching idea of anything. In our company, it's wheat, it's canola, lupins, and barley. In any other company, watermelons, chickpeas, whatever. This is the whole idea of what they're actually trying to achieve. So why do you breed? Now, it can be for many reasons: climatic changes, desirable traits such as herbicide effectabilities, new herbicides coming on the market. You need new genetics in there. Disease strains change. So there's a new leaf rust strain that's come over from the east in the last, I think, 2 or 3 years. So we have to keep on top of those. Pathogens or pest prevalence, so Russian wheat aphid, the big scare that we had a couple of years ago with that as well. Now, do we have the genetics needed to combat these increasing pests? Emerging markets, if there's a new quality trait or if there's a new quality style that the market's asking for, that's not a bread wheat or it's not a noodle wheat, I don't know what it could be, but it could be something else, we could then breed for that. And the main one about why we even bother about breeding is so we can get more yield. So we can get more money back to farmers, and therefore there's more EPRs for us to reinvest into more money back for farmers, so the cycle continues. This is overly simplifying it because I'm the marketing bloke, I can do this, but if I was a breeder I'd probably get punched. Anyway, so this is the 6 key steps for breeding, as I see them. So you've got to determine what you're actually looking for. So what's the aim? Then you go and find what the parents that have that aim, you cross them. So for example, if you're looking for a higher sprouting tolerance, you'd be looking towards S-stock or a Yippee type. So you cross that with some of your other wheat varieties that you're trying to bring up. Now you combine the genetics, so that's crossing in the glasshouse. Then you get all these crosses and you look at them all, and then you start deciding which ones look the best and are doing exactly what you want them to do. That part's called the selection. And then once you've selected them, you actually plant them out in a whole pile of trials to make sure they're doing what you thought they'd do. So that's the wide-scale testing. And then you bulk it up to a certain amount that we can actually release to the farmers, and then you guys can have a crack at it and grow it in your own paddocks. So that's the release. And what sort of time frame does that actually look like? You make the crosses, then you've got 3 to 6 generations of inbreeding to make it a genetically pure line so it's stable and does what it's supposed to. Then you have 4 to 5 years of yield testing, disease testing and quality testing, 2 years of NVT testing, and at the same time as the NVT we're generally doing a year or 2 of seed multiplication to get it to that level so we can release it. So this all takes from about 10 to 12 years from cross to release. So although we're saying we're working on something quickly, it's still 10 years out if we cross it tomorrow. So that's quite a long time to be doing some stuff, doing all the breeding. Some other challenges that we face with breeding, there's lots of error. So not all environments are the same, and not even all paddocks within the paddock are the same. I'm sure all of you have noticed that some of your paddock has soil type changes within 10 metres and you have to deal with that on a yearly basis. Are we doing the same thing as the farmers? And which farmers are actually doing the right thing? And which ones should we be emulating? All this reduces the accuracy of selection. Yield plots are expensive, and you can only get 1 yield plot per place per year, so they're quite slow as well. Quality testing, you need a certain amount of grain before you can actually put it through a lab. They're looking for kilos, and at the start of the program you're dealing with grams. So there's a disparity there before you even begin as well. We don't always have the genetic variation that we need, so frost tolerance, which you guys spoke about this morning, we don't have all the variation we'd like in the programs to be able to make the next step with that as well. Take-all resistance is another example for that. And you can't always select for the trait if it's not there. So Russian wheat aphid, it's hard to screen for that if we didn't have Russian wheat aphid. Quality at the early stages, as I mentioned, because we need such a large amount of seed. And rust, you can't get the rust score on a new variety if there's not any disease or any rust there present. So this all boils down to a few key words. Accuracy, this one's all about changing the error, making it accurate. This is all about speed and time. This is diversity, and this is scale. And lo and behold, we've actually just identified the 4 levers that you can actually manipulate in terms of changing the speed and scope of a breeding program. Essentially what we're doing is this, sticking our head in a giant pile of, looking for a needle in a haystack, giant pile of hay there. So by manipulating accuracy, speed, diversity and scale, you can either make the haystack small, or you can put a lot more needles in that same haystack, and then you increase your chances of finding those elite guns or the next scepter. So accuracy. So previously we used to have to bag up every single plot, put it in a paper bag, take it back to the lab, weigh it, enter it into a computer. Now we have headers with integrated onboard weighing and data capture. So what used to take weeks to get data and results, we now can do in hours. GPS tripping, so we used to have to do everything by eye, so the tractor driver would have to be driving the tractor by eye, which apparently is quite a skill that I never had the joy of doing because I'm terrible at it. I'm very reliant on GPS. We also have the plot seeders being tripped by the GPS, so then we know exactly where the plot's going to go before it even goes into the ground. We can use complex stat designs for the trials, so we can have higher accuracy and use more powerful statistics over the data to make sure we are identifying those needles in the haystack. And by having a robot load the trials, there's less human error, and this way we can actually make these complex stat design trials because the robot doesn't whinge that it has to do a whole lot of different things each time you put in one single variety. So this is what it used to look like, a couple of blokes sitting on the back on Hessian bags for some strange reason, and pouring seed packets into seed cones there, lifting them manually whenever that bar down the bottom crossed a certain line for the plot length. Also, this bloke here was driving by eye, So although it probably was pretty good and it did work for the era, we can do it better now. This is the weighing of every single one. That's one single plot in that brown bag. So we have thousands and thousands of these coming into a lab, and we have to weigh them manually, enter it into a computer. And so obviously there again, it takes time, human error, less accurate. So now we're dealing with custom built seeders that can seed 2 rows at a time that are tripped by GPS. GPS on the tractor, so it's, again, there's no issues with driving. These headers up here are all cabbed, and they're the ones that I was mentioning that have the onboard weighing and data capture systems, so then we don't have to worry about bringing it all back in the trucks. We can actually weigh and discard and rip through a lot more plots in a shorter time frame. This is the robot that I mentioned. So each one of these little cells is one plot. That's the easiest way to describe it. So one NVT plot that you guys have seen and know is one of those cells. This robot can load a certain amount of plants per plot, so you can punch in what is the seed number or the seed weight of the line you're dealing with, and you can make it a lot more even and a lot more accurate. So there's no variation between the plots because of the seed number. So we're eliminating that error as we go along. And I've got a video of it in action. If it I don't think so. Sorry, this one doesn't need sound, but the next one will. Yeah, as you see there, so it's going along and it's going to have the randomised design that's very complex, and the robot is working in a matrix and it knows exactly what plot, range and row to put it into. So by doing that, like I said, it's highly accurate, the stats you can put over top of it. Did I just jump over one?
No,
No, sorry. Another lever that we can manipulate is the speed and time. So we can have more than one generation in a year. So we can do this by having a winter crop, summer crop, winter crop. So we can really speed through a few generations. We did this with Scepter to get it to the market as quick as we could because we identified how great it was, and we thought, well, we want to get this to the growers as quick as we can. So that went over summer, or winter, then summer, then winter. We also use growth rooms, which take care of the temperature requirement of some of the plants to really fire them through their growth stages, so vernalisation. And also they're on LED lights, which are the right wavelength of light to trick the plant into thinking it's daylight for 20 or 22 hours at a time. So it can really fire through the generations. You use this in the early stages of the breeding program. You're not trying to grow a whole big plant, you're just trying to get from seed to seed as quick as possible. So they look quite spindly. I've got a photo of that in a second as well. Genomic selection, so marker-assisted selection. I'm sure you've heard of markers before, or everyone has a whole pile of, or a genome. Wheat has a very complex genome as well, so we have markers for certain traits that we're looking for and trying to identify. For example, again, Scepter, it has a leaf rust gene called LR46. So we scan the whole genome of Scepter, it pops up a flag at LR46 and goes, righto, I'm here. So good, well we know that LR46 is present. The leaf rust gene is going to be quite comprehensive again against most of the leaf rust strains that we know of in the market. That's the old way of looking at markers. Now we can actually get all those markers, give them a smaller value for each one, and you're scanning not one marker on a single gene, but you're doing tens of thousands of markers, known and unknown, to give a prediction on how this variety is going to go compared to other varieties in the field. Now, it's quite complex and it's quite cutting edge, and we're actually the world leaders in this, which is way beyond half my comprehension half the time as well. But it means that we can, between generation 2 and 3, we can take a snip of the leaf, send it away to a lab, get the DNA marker screened, put it through our GS stats program, and before it's even gone to seed that year, we can work out if it's going to be a high yielder of the Scepter, or if it's going to be a lower yielder, if it's going to have good quality, bad quality, disease resistance is high or low. So the idea is that you shift your breeding program further away from the crap. So you use this data, you don't actually look for the good ones, you get rid of the bad ones. That's quite an easy way to think of it. You put a broom through it, shifts the genetic potential of the whole group of what you've got in your program further along. We also have what's called high throughput phenotyping, which is quite a tongue twister, but this is about using, phenotype is obviously the growth habit or the look of a plant, so how you can use optical equipment and data to replace taking measurements in the field. This is the growth room, as I mentioned, so as you can see there, they're not the most, they're not massive big leafy plants, but all this thing is trying to do here is going from a seed to a seed. These are the LED lights that are the perfect wavelength, so the plant gets as much light as it can, more chlorophyll, keeps firing through, and the temperature is constant through for perfect growth conditions. Now I have a video to explain the high throughput phenotyping. One of our PhD students, James, explains it quite well, so give that a go. I think we've got sound out.
Various types of technology to collect and analyse data from large...
Right, we'll start that one again, sorry. That's awesome. Good.
Would be nice to go to. Never hear that.
Yeah.
Hi, I'm James, a PhD student from the University of Adelaide, where I'm working closely with wheat breeders from Australian Grain Technologies to investigate how we can use various types of technology to collect and analyse data from large-scale field trials like this one. The main part of my work looks at how we can use sensors such as digital cameras and LiDAR, which is like radar but using light, to collect data from tens of thousands of field plots, and ultimately how we can use that data to help plant breeders select which of these plots could be the next variety for farmers to grow. To do this, we use a prototype imaging boom we've created, which is attached to a tractor and driven through these large field trials. As the tractor drives along, the cameras and LiDAR automatically capture photos and a laser scan of each individual plot in the trial. All of this data is being controlled and captured by a GPS unit and laptops in the tractor cab. Once we're done out in the field, we can grab that data out of the tractor and head back to the office to start processing it. The LiDAR data is processed using code written in the R language, while the photos are processed with software called ImageJ. Once the data has been processed, we can measure basic traits such as canopy cover and canopy height. But we're also looking at using the LiDAR data to make 3D reconstructions of the canopy and measure more complex traits like crop biomass. So that's some pretty nifty data collection that we're doing. But what does that mean for breeders and researchers out in the field? Well, it means that we can start to replace these time-consuming and often subjective manual data collection methods with these quicker and more objective digital methods. There's also the potential to eliminate destructive sampling, which is generally too impractical to use within a plant breeding program. Most excitingly for plant breeders, instead of measuring a few trials in the breeding program, they'll be able to measure all of their trials and every plot within those trials. This will provide a really powerful data set for them to use, especially when it's combined with genetic and environmental data.
So as I mentioned before, one of those plots is one of those cells in the robot loading bay. And across WA we have about 80,000 at least of those plots across our breeding program. And across AGT nationally we're upwards quite comfortably of 300,000. Now to put that into perspective, all of France is probably around 120,000 plots for wheat. UK is around 70,000, so we are really trying to push the envelope as fast as we can, get that genetic gain faster so we can get those better varieties, those elite varieties, into farmers' paddocks as quick as possible. Now diversity, as I mentioned, so you don't always have the the diversity in your germplasm that you want, so you need to go look for it. Now you can do this through varied crosses, bringing in a whole different mix of genetics. Locally sourced, so varieties that are out on the market we have access to. Locally, we also have access to pre-breeding efforts from GRDC. They have a few projects that we can use, some of the universities and CSIRO as well. We also have international linkages with one of our shareholders, Lima Grain. They're one of the biggest wheat breeding companies and plant breeding companies in the world. So we have access to their germplasm, varieties and breeding lines as well. So all of this is just an idea. If you think of plant breeding as a pyramid, the top is where you're looking at your scepters and your elite lines. Down the bottom is basically all your breeding lines and crossing to get the new genetics in. Trying to widen that base of that pyramid as much as you can. You get a whole pile of diversity in there. Then you're stacking the needle in the haystack with a lot more needles, or you're making the haystack actually smaller. Now scale, as I mentioned, you can't always test for everything you want in a location, so you go and find that location where you can actually test for it. We have dedicated disease nurseries. There's Rust Nursery in Carnarvon, there's one in Coverty, there's also one in Roseworthy. There's Black Point and Powdery Mildew Nursery down in Esperance, and then there's also a Yellow Spot Nursery that we put in Northam. Now these just are a few that we have around. There's many more different disease nurseries around Australia. One of the big advantages of being a national company is that we screen all our stage 4, or the stage before they go into the MBT, which is what we consider our elite varieties or elite lines. We screen everything across Australia in every location across Australia. So if a New South Wales line performs really well in WA, then we'll release it. That actually happened with Korak. I'm not sure if anyone can remember Korak. Also, some stuff from WA that's done really well over east, then they can release it over there as well. So the scale that we have is actually plays in our favour, so we can get the best genetics. It doesn't have to be bred from that local area. It generally is, but it doesn't always have to be. And as I mentioned, increasing the base of the pyramid, so we increase the breeding program, or the early generation part of our breeding program, to really fire across the genetic potential of the lines. This was just an idea of the scale. So this is our Northam site a couple of years back. It's probably about 1.5 k's long and 300 and something metres wide. So that's our home site where we do a lot of the early generation work. This is Roseworthy's home site from about 2010 from memory. Also have a video on CRISPR to show you just not only the genetic potential, not only the breeding efforts that are going into CRISPR and how they can be used, but it's quite a complex idea to get your head around, and this video I thought explained it better than I ever could.
Scientists have long imagined being able to make specific changes to the genetic code of a cell or organism. A revolutionary genome editing technology makes this possible using an RNA-guided protein called Cas9. Cas9 searches through the cell's vast genetic material until it finds a sequence of DNA that matches the sequence of its programmable guide RNA. The guide RNA enables Cas9 to open the DNA helix, then to position 2 molecular blades to cut each strand of the DNA double helix. Repair enzymes seal the gap in the broken DNA, sometimes by inserting new genetic information supplied by the cell or the experimenter. In this way, disease-causing mutations can be corrected by changing the underlying genetic code. Scientists are now using this Cas9 technology for research applications in human health, agriculture, and bioenergy.
So where CRISPR has the application of CRISPR is quite exciting is when you have targeted changes on a genome. So this is really good if you know the markers you're looking for and you know the actual site of the genome you're looking for. That's the limitation of CRISPR. If the trait is controlled by a single gene or a couple of genes and you know where they are, like I mentioned, then you have no issue changing them. You can pop in that LR46 leaf rust gene I mentioned before into a variety that had everything else perfect, but that leaf rust gene wasn't strong enough on its own. You could punch in another one, that's where it fits. Or Clearfield, it's only controlled by 2 genes. We could easily manipulate Septa to be Septa Clearfield. It's unlikely to work for genetically complex traits, so yield, it's tens of thousands of genes, and we don't even know any of them really, to be honest, that control yield, so you can't just CRISPR in more yield. It doesn't work that way. And frost tolerance, which I'm sure you probably heard about this morning. Hopefully I'm not saying something contradictory, but there isn't a frost gene that we can go in and target and rip out and put in the frost gene. So again, Septa frost. Unfortunately, it's just not the way it works yet until we have all the genes mapped. So where I see it having quite a big fit is those simple or a few trait genes that we can control, and it'll be a tool in the breeder's toolbox. We'll never have a CRISPR breeding program on its own. It'll be a part of our breeding program that also works in conjunction with the summer nurseries or the yield plots. So all in all, the target for plant breeding, as I mentioned, is this greater genetic gain. So getting that productivity and profitability quicker into farmers' hands than sitting in our program. Through all these 8 different ways that we've mentioned, so the breeding equipment, the DNA selection, robots, stats, next-gen phenotyping, James driving around with his tractor, gene editing such as CRISPR, and multiple generations in international germplasm that we have available, we feel that we can actually shift the genetic gain further and quicker out in our direction, and hopefully in that way get growers, yourselves, a better variety even quicker. Thank you very much.